In part 3 of the sorting unit, we'll look at a few other divide and conquer algorithms. None of them is technically a sorting algorithm, but because they have some similarity to how our key sorting algorithms work, namely merge sort and quicksort, they fit in this unit to round up a bit on what you can do with divide and conquer. So let's see more concrete examples in a minute. I want to briefly comment on the name. Comes from a Latin phrase and is used in slightly different meanings in different fields. It has a maybe slightly negative touch if you use it in the politics sense. In particular, you kind of seed disagreement. We don't try to do that in algorithms, but somehow the term got stuck. Some of the terminology in computer science is just because people had a strange sense of humor sometimes. And once a term is established, it's a bit challenging to change it. This one's not as bad. I'll have another example later in the course where I decided to rename things. For us, in algorithms, divide and conquer really just means this rough, vague principles of breaking a larger problem that we're trying to solve into smaller independent subproblems. So I think the important bit here, many algorithms somehow break a problem into smaller parts. For divide and conquer, what we stress is that these are independent problems that you can solve independently. And we also usually assume that they kind of cover the entire problem. For the experts, this is to distinguish it from dynamic programming. We don't really have to do that here. So you somehow identify subproblems, you solve them recursively. So usually divide and conquer algorithms can nicely be described as recursive functions, but you don't have to. And then there's some step of putting things together. We've seen various examples. We didn't talk about this in detail. I can tell you offline if you're interested. For merge sort, the breaking into steps, into parts was very easy. We just split in the middle. In parentheses, unless we want to do peak sort, but let's ignore that. So we just split it in two, so the breaking up was very easy. And then when we come back from the recursion, the merging was the part where we spent most of the time. And quicksort is a bit the opposite way around. We spend a lot of time of dividing. With partition, we do the main effort up front. And then we obtain the subproblems as part of as the output of the partition. And binary search, you could say, is also a kind of divide and conquer, but you only follow through with one of the subproblems. If you want, you can put it in the same framework. Right, so apart from the names, let's see some concrete examples to make this a bit more concrete. And one is this idea of order statistics, or also known as selection or selection by rank. To motivate this a bit, a standard thing you want to do if you have numeric data and it's a bit too big to just look at it. I'm thinking here of one-dimensional data, so it's an array of numbers, or one big vector. There's a few standard things that, for example, tools like Pandas, this Python framework that maybe some of you have used for data science tasks. It has a standard method describe that gives you pretty much some of these functions. And it's a standard practice to, if you have a large data set of numbers, to just look at these summary statistics first. So I'm sure you know what mean and standard deviation are, and min and max. Slightly more esoteric, but often very, very useful, are these order statistics, for example, the median. And the median is just an element, so that half of the elements are smaller and half of the elements are bigger, with breaking ties in a reasonable way. So you have to make that a bit more precise, and we'll actually do that in a way when we define our algorithmic problem. Apart from the median, you can ask for other quantiles. For example, quartiles. A quartile, the lower quartile would be a value so that a quarter of the elements are smaller and 3/4 are bigger. Then there's 2 other quartiles. The second quartile is the median, and the third is 3/4 are below. And you can generalize this, of course. Now, if you look at this from an algorithmic perspective, all of these are easy to compute in linear time. For histograms, at least assuming that the range is, that the number of bins is small. For the order statistics, it's not obvious how to compute them in linear time. And so that's what this problem is about. So more formally, we call this the selection by rank problem. And the input are 2 things. It's an array of numbers, or actually general objects. Another thing I didn't mention here too much, but you can only define a mean on numbers where you can do arithmetic, where you can add up numbers. You can define these order statistics for arbitrary objects that you can put into a relative order. So these are more general. You can ask for the median of all last names in alphabetic order, and you can check what letter comes first in that name. It doesn't make sense to ask for the mean value of your last names. I mean, you can maybe define something, but it doesn't make so much sense. So these are a bit more general as well. Okay, coming back to the problem definition. We have an array of numbers. Let's keep it simple for this one. And we have a number that's the position that we'd like to have. And the way I formalize this is, suppose you would sort the entire array and then look at position k, at index k. So we'll use this with the same kind of convention we had before. It's all 0 based. Then the answer of this problem is, what would you find at index k if you sorted the entire array? So if you put n½ in, rounded appropriately, you get the median, you get the quartiles, and you can find minimum and maximum, or the elf largest, by putting k to the appropriate value. Now, an obvious conclusion to solve this problem is you just sort the array and then pick out the number. So I didn't even put this on this slide, but if you're willing to spend n log n time, then we already know how to do this. Just sort the entire array. The whole point of studying this problem in isolation is that you don't actually need to sort the entire array. All you want is that one element at its specific position. And it turns out we can find that much cheaper. If you've seen this before, the algorithm is called quick select. Maybe you know this. But let me introduce it anyways from scratch. So the way to motivate this, if you haven't seen it before, I would say is like this. If you're given a rank, it's not easy to find the element that has that rank. But if you're given an element, computing its rank is easy. You just count how many elements are smaller. And so in a way, quick select uses one to do the other and shows that they're in some sense not as different as they first look like. So what do? We pick an arbitrary element and find its rank. How do we find the rank? Well, we count how many are smaller. If we, by accident, happen to pick the right element, that we were looking for, then we can stop. And otherwise, we have learned something. Namely, if the rank of this element that we picked is too small, then we know all elements that are even smaller than that element will also definitely be too small, have too small a rank. So we can exclude all of those. And that actually includes that element that we picked itself. And because it's zero-based, that's j plus 1 elements that we can exclude. And the symmetric case, if the rank of the element that we picked is too big, we can also exclude a lot of elements, hopefully. And maybe no surprise at this point. If you want to find how many elements are smaller and also exclude them afterwards, well, you really want a partition. So we can use exactly the partition function from quicksort to do both of these things in one go. We find the rank of the element by the return value, namely the position where the pivot went. And that procedure already nicely separates the smaller and larger elements. So we can use the very same kind of subroutines, which is why I did not spell this out. If you scroll back 200 slides with all the animations, which I don't want to do now, you find the code for partition. Right? We covered that in the quicksort section. And we also have this method to choose the pivot. That's in a way the same kind of story as for timsort, for quicksort. I'm getting mixed up. It's the same story as for quicksort. You don't want to pick a fixed element necessarily, because then you might be vulnerable to a worst case. You could pick a random one. That's not a bad choice. And you can do compromises on this in practice. Well, let's suppose it's some arbitrary function. We get the pivot, we partition, we get the rank of the element of the pivot that we picked. If we were lucky, we can just return that and stop. And otherwise, we have only one side of the recursion to still pursue. So again, if the rank of the pivot was too small, we can ignore all the elements that are even smaller. So we'll focus on the right half of the array, or the right part. It's not necessarily half, right? And otherwise, we focus on the left part. One small point: if you have to recurse on the right side, you have to adjust the rank that you're looking for, because you're excluding elements. And so in the way I formulated the problem here, you have to adjust your rank. How good is this? So maybe not completely obvious, but if you think for 10 minutes about it, you see the same worst case as for quicksort can happen. Suppose you're trying to find the minimum in the array, so your k is 0, but because the universe conspires against you, you always pick as pivot the largest element in the array. So in each round, you exclude just that single element, but you pay a linear cost. And so it gives you the same worst case as for quicksort. On the other hand, the expected cost is actually linear. It's not n log n. It's way better. And the reason is we don't do the second recursive call. We always just do one. And so you have to be constantly unlucky with your pivot choice to see a high cost. It doesn't need extra space. It actually doesn't even need recursion. If you look at the code here, we only do one recursive step. So by rewriting the code, making the code a little more messy, you can make this one big loop. You don't need any recursion. And so you can do without any extra space. You can also tweak the same code to find, say, 5 different order statistics in one go instead of just one, which is a bit more expensive than finding a single one, but it's cheaper than calling quick select 5 times. But that part's not so vital. So for practical purposes, quick select is fine, and the programming libraries that provide a method for selection by rank, like the C++ library, the standard template library has a method function nth element that is based on quick select. We'll meet those two characters in the next unit a bit more. So I tried to make this a bit of a dialogue between the practitioner programmer, who's happy if it works most of the time and in most applications, and the kind of theoretician that says, I also want to have these provable guarantees, the eternal truths of algorithms. So he's not quite happy yet, because it's such a fundamental problem. Can we actually do this in guaranteed linear time, worst case linear time? And it turns out the answer is yes. This is one of those problems where a lot of really smart people, Turing Award winners, Turing Awards are our Nobel Prizes, so that's the highest you can get, didn't know in the 50s, 60s, they were pondering over this question. And then it came as a sort of surprise, I think, at the time. That's what people told me. They're still alive, So it came as a bit of a surprise initially that this is possible. I'm just trying to talk it up a bit so you appreciate maybe it. Now it's a decade-old result, and everybody's just shrugging their shoulders. Of course it is possible. But maybe it's not so obvious. We can pick our pivot more carefully, and then we get worst-case linear time. But to do that, you have to be a bit careful. So we'll work our way towards it. First of all, what this weird spiral is trying to show you is a geometric series, right? This is just showing that if you sum up 1/2 to the I, starting at 0 and up to infinity, that's the area that I drew here, right? We start with 1, then we have 1/2, then we add a quarter, an eighth, and so on. As you can see, the arrangement of the spiral always leaves enough space for the next little rectangle to go in there. So the total area is 2, and it converges to 2 if you keep going. That's just elementary stuff. So I just like the picture. Sorry for that. So if we somehow can guarantee that, right, I should probably connect this to quick select. Why is this relevant? Let's do this in the code. What is the cost of this code? Choosing the pivots, at least the way we've done it before, wasn't very expensive. The key point was that the partitioning method uses linear cost, linear time. And n here would be the difference between those two. So we pay linear time for doing the partitioning step. That would be the first partitioning call. And we multiply the whole thing by n. So if I have an n in front here, I get an n here. I'm just multiplying it all by a factor n. So if the first partitioning call has cost 1 times n, it would give us the area of that box. Now, if we somehow achieve magically this, that the pivot is the exact median, I'm starting with the entire list, and I'm cutting it in half exactly. So whichever way the recursion goes, the worst case is that I still have to look into half of the elements. So the second partition call will have 1/2 times n the area. And so that's what we add. If you keep going like this, if you always select the median, no matter which way the recursion goes, you will always have as the next cost something that's half of what we previously had. So the total cost is summing up these powers of 1/2 times n. And that sums up to 2 times n, which is theta n. That's linear. That's great. We like that. So that means if we get a pivot that's close enough to the median, we can do selection in linear time. Now the problem with this approach is, finding the median was the original problem, or it could have been at least. The whole problem was selecting by rank. And now I'm telling you, oh, fine, it's solved if you give me the exact median. But that's the original problem, so it seems useless. It isn't useless because we don't actually need an exact median. So we can do something more fuzzy. More concretely, if you fix some small number epsilon, so some constant number, say, I don't know, epsilon is 0.01. it's enough if our pivot is in this range. It just shouldn't be too much extreme. It shouldn't be too close to either of the endpoints. And the way to show this is using the same kind of argument. You start with the full array. Now, in the worst case, your pivot is right here at the boundary of where it's allowed to be, but you still lose this epsilon n elements, and you recurse on something of size 1 times epsilon n. Here you again split off, in the worst case, at least these epsilon n elements. So what you recurse on is 1 minus epsilon squared n elements. So if you keep summing that up, now the actual algorithm would never go to infinity. It would stop at some point. After at most n steps, it has to stop. But we can upper bound that standard trick. We can say, instead of bothering with this upper bound here, I'll just be more generous and go all the way up to infinity. And that you can simplify as 1 minus epsilon, which is just 1 over epsilon. So if we pick our epsilon very small, this is 100n. So it's a bit bigger than 2n, but it's still linear at least. If we can somehow guarantee that this is a constant fraction away from the endpoints. Okay. Is there a question? So you have to scream. Why can't I use what? Hashing or caching? Caching. I don't see how you can use caching. Let's talk afterwards. It's not. I don't hear well in the distance, and maybe it takes us too far away. I don't see how you would use caching. So the partitioning you do is different each time. I don't think you can remember much. Let's discuss it afterwards. I don't think it's effective use of the time. It's better one-on-one. Let me show you the solution, which again, it looks a bit messy, but it fits on one slide. So it's manageable complexity, but remember again, celebrated by famous people at the time. The way to choose the pivot is to use the algorithm recursively in a tricky way. So where we choose our pivot here, we call this function. And what it does in conceptually is you have your array of all the elements. I'll probably need more, but yeah. You take groups of 5 and find the median of those 5. So say this is the one. And then you keep this guy separate in the front. Then you take the next 5 elements. It's a tiny example, so yeah, we'll only get these 2. So you take groups of 5. That's what this does. We can be generous. It's a small thing, so we just sort that entirely. And then we take the middle element, that's the median of those 5. And we move that to the beginning of the array. So once we're done, we'll have the first fifth filled with all those medians. And the rest is, well, sorted groups of 4, but we'll actually ignore that. Now, to find the pivot, we take the exact median of those 5 elements, of these, the medians of 5. So in this case, it's 5 elements, but that's kind of a stupid coincidence. Let's make my example a little bigger. Okay, so this is just a fifth of all elements, but we recursively call our algorithm on this. Once we come back with that pivot, the rest is as in quick select. No changes. The only change is that I renamed the method. And a few things to point out. First of all, we do 2 recursive calls to the function, but from 2 different places. So these are 2 mutually recursive functions. This one calls itself recursively, but it also calls this function, which again calls that one. So it's a bit of a messy relationship, but you can do this. It's standard practice. But it means we essentially have 2 recursive calls. And remember, that's potentially dangerous area, danger zone, because that might mean we need time n log n, not n. For sorting, we had 2 recursive calls, and the overall time was n log n. But we know that this innermost call is only on a few elements, only on 1 out of 5. The second recursive call inside here is on the left or right part of the array after partitioning. And we don't exactly know how big that is. But we can give an upper bound on how big it can possibly be. And that's what this picture tries to do. So you have elements arranged in these groups of 5. That's what this part does. That arranges elements in groups of 5 and picks the median. So the final pivot that we choose is this one. That's what we get back here from that method call. And what can we guarantee about this median? It's bigger than all those elements and smaller than all those. And each of those in turn has at least 2 above it that are smaller. Each of these has 2 that are below it that are bigger. So transitively, this pivot is bigger than at least all these elements in this left upper blob. And how many are there? If you draw this to get to this number, if you draw this a bit more abstractly and continuous, the median is picked from the middle, and then we have these 5 rows, and basically we're looking at this part, which is, it looks like a quarter of this rectangle, but it's actually more, right? Because it's 3 out of 5 rows, but half of the width. So that's 3/10 of the overall elements. There's a plus minus a few elements that you have to be more careful about if you want to rigorously prove this. But for this part, we'll leave it with the asymptotic equivalence statement. Right, so again, this is length 5 in total. The total rectangle here has length n/5. Then the black part, that's n/5/2. And the black part here is 3. You'll have to zoom in to read that. So it's, if you multiply that out, that's what you get. And then we can at least roughly upper bound the total time as follows. We do a similar approach as for merge sort back in the day, where we said there's a recursive function c of n that gives us the cost of merge sort applied to n elements. There's a linear term that comes from the partition. So remember, it's not actually merge sort. We're doing something closer to quick sort. So this part comes from the partition call. And from these parts, so we're sorting little parts of 5 elements each, but we're doing this for the entire array. That gives us some linear cost. And then we have 2 recursive calls. This one is the one up here. And the other one is the one down here, either this one or this one. We only have one of the two. And we can upper bound how big the parts are that we recurse on. For the blue one, we know exactly because it's every 5th element. And for the orange one, we know it's everything but this black part. So all elements apart from 3/10 is the same as 7/10. And now this next step, don't do this in general. It's only true because we can make the guess and then prove it correct that the function is upper bounded by a constant times n. But with that assumption, we can pull these two together. So instead of having 2 calls on 2 parts, we do 1 call on the total size. And that can only be more expensive if we do that. And if you sum that up, we get something like this. And so we spend linear time, but then we recurse on something that's a constant bit smaller. So if you remember what we did before, that's exactly the situation I drew here, except that our epsilon is actually 0.1, not 0.01. So what we'll get as result will be 10 times n. And so that's how you get linear time for this. That's the median of medians algorithm. So it's a deterministic algorithm that always has linear time, worst case cost for finding any rank in an array. As part of the more sophisticated divide and conquer algorithms. So you don't need to know the analysis in more detail than what I showed here. There's 2 places where to make that formal needs a bit more work, and I don't want to do that here. So you only need to know it at this level, and I think if you roughly know how the picture works, you'll be good. I mostly want to keep the knowledge that there is a deterministic selection algorithm with you.